thank you for the introduction, and thank you, organizers, for invitation and support. This is my first time here. This is a joint talks actually with Leonid Slavin and Vasily Vasyunin, but the subject is old. It's about Bellman function. Leonia Slavin did a couple talks on different meetings, and he had like 20 minutes. So his talks mainly was about the heavy part, the hardest part of the method. And you might be impressed by the complexity of the method after his talks. But my goal is to depress you with simplicity of the methods and approach on simple examples, so totally opposite. So first of all, let me start to see if this technology works from this position. No. So I probably should move here. Not yet. Oh, I'm sorry. Yeah. So first of all, contributors. And so historically, we can attribute the invention of the methods to Burkholder and David Cox, who use this in martingale settings. And that was, I would say, ancient age for the methods, and main contributors here: Burkholder, Cox, Banuelos, Gang. And then, and it was about 80s. In 90s, the legendary team of NTV, Nazarov, Trail, and Wahlberg, and their students, they invented the Bellman function explicitly and push forward the technology. And I would call that it was a kind of renaissance age for the methods. And the modern times started with works of Slavin, Vasyunin, and Melas, when explicit functions were computed and was developed some methods and actually machinery how to do it. And then some other people did good job, which are listed there. So the source for the methods mainly is in martingales. And what's good about the martingales is that we have a natural nested sequence of scales. And this means that from the definition of a martingale, you can see that the martingale, it's from the definition, it relates the value on the previous scale with the value on the next scale. And so the induction in scale is something which is very natural methods in martingale theory. The main theorem in martingale theory is Dup's theorem, which in the simplest way, in simplest version, says the following: that if you consider a maximal martingale operator, then it's in the simplest settings, discrete settings, that it's bounded. It is bounded in LP with a sharp constant Q, and if it's infinite sequence of martingales which is uniformly bounded, then there is this limit, almost sure for that sequence of martingales. And you can look on this statement like on Fatou's theorem. So Fatou's theorem says that if harmonic function is bounded, then there are boundary value almost everywhere. And here you see that if martingale is bounded, there is limit almost everywhere. Moreover, you can see on martingale difference as an analog, discrete analog of derivative. And this explain why martingale theory somehow related to harmonic analysis and vice versa. And there are more sources. Say Haar system, it's well-known statement of Pelle that it's in a conditional basis, which could be written saying this way: if you take any Haar polynomial and multiply coefficients with any choice of plus or minus, that you cannot increase the norm of the new polynomial much. It should be in this form. This is a relation which relates, and you see the constant C depends on P, but it depends, of course, on the, you can extend it to more general autonormal system, and then that constant will depend on the system if it has this property. And Alevsky, Alexander Moiseyevich Alevsky in 1967, he proved a statement then among all orthonormal systems with that properties, the best constant is for Haar system. It cannot be better. So the lowest this unconditional constant is for Haar system. And so this system, the value of this constant becomes important, right? Because it's kind of universal constant. It's about this mathematics, if you wish, about this universe. And it was computed by Barholder in 1984. And it turns out that this value is P star minus 1, where P star is a maximum of P and conjugate exponent Q. So, you know, in a modern language, people would say that after these two statements that Alevsky meet Barholder or something like that, which in fact never happens. They never communicate to each other. But this is really a very important result, and it has tremendous impact on analysis. And you know, Barholder introduced UMD spaces and proves that singular integrals are bounded in Z spaces, and then and it's considered like a simple part, and then Bourgain proves the opposite statement. So UMD spaces are spaces where singular integrals are bounded. And after that, the proof here involved Bellman function in a modern language, while Barholder didn't use explicitly the term. But in fact, it was the first time when he explicitly compute some function in a very tricky, very involved way. And that function is a Bellman function for some problem which was pointed out by Wahlberg later. And you see that if harmonic, in all that theory, Haar functions are involved in almost each papers. You can see Haar decomposition. And the explanation, one of the justification is the following, that if you decompose the function f into Haar, Fourier Haar series, and take a partial sum that they, of this time, that they form a martingale sequence. And say you can choose dyadic maximal operator, which is just an averaging over dyadic cubes and taking a supremum. You can treat it as a supremum of partial sums. And then from the point of view of harmonic analysis, if you have a maximal function, should be a singular integral which this maximal function controls. And what's the difference between maximal function and singular? You should remove supremum and put here some condition which means cancellation, right? And this is the difference between maximal function and martingale and singular integrals. And this means that if you remove here supremum and put here plus or minus, this is so-called martingale transform, if sigma is a sequence of this plus and minus. So you can see on these two things, like on martingale version or stochastic version of maximal function and singular integral, and so you can do harmonic analysis and problems similar to harmonic analysis problem with this stuff. And This way we can get something which is now a very popular subject, dyadic harmonic analysis, when you can get something from harmonic analysis, just trigonometric, from stochastic analysis, and do good job here, get Betz constant and some other proof, and then try to go back with that to the trigonometric case, the classical harmonic analysis. Another example is conjecture of Ivanitz that the normal Berlin-Arthur operator is P star minus 1. And he proved it, he conjectured this in that paper. Actually, with Gavel Martin, he proved that it cannot be less. And then Banuelos in 1995, he proves the norm cannot exceed 4 times P star minus 1. And then Nazarov, Wolberg, they changed this 4 to 2. And then with Dragicevic, they show that in P large it could be like Z1. And maybe they have something better, I don't know. But that's a really good examples of application of Bellman function techniques and methods. Some other achievements, for example, for the dyadic maximal operator here, MD, it's possible to prove that in Dupl inequality you had the value less. Actually, if it's F non-trivial, that there is no maximizer. And it's interesting that Hardy himself proves that same time inequality for one-sided maximal function, but for standard two-sided maximal Hardy-Littlewood function, it's an open question. We don't know whether it's true or not, as far as I know. And another example of application is celebrated paper Wolberg and Peter Michel in Duke of 2000 with some statement, and Stephanie were awarded a Salem Prize actually based on these results mainly. Some other good examples are computation of explicit Bellman functions, which is pretty tricky stuff, but for very good, you see, for John Nirenberg, for Mackenhaupt, for Rivers-Hilder, Dupl inequalities, they were computed explicitly. And another example, say, recent work of Christina, when she proved some sharp estimates in terms of dependence of the weight. So what a big idea? A big idea is very simple. Convexity plus induction on scale. Induction on scale is coming from martingale settings. And convexity is something which is well known in analysis. So there are books of several books when convexity is used to prove some inequality. So if we combine that idea, we will get roughly Bellman function techniques. For example, for the Jensen inequality. So if we consider a function on the interval I and fi is averaging, and if you split I in two equal pieces, left and right, and denote it I minus and I plus, then the same for the averaging you will get that statement. And if phi is convex function, that phi inverse, this is the inverse for the 5. It's concave down, actually. And these are values. So what's important is that the average of z and z give you the middle one. So the average at this point and at that point give you, the average of these two in X give you that one. And if it's convex, that you will see that the value at the middle, which is written to the right, greater or equal to the averaging of the endpoints. And geometrically, it means that this point is above that point, right? But this is for inverse function for phi minus. And if you continue doing the same way, apply the same inequality to each point, so the next step, you split the Z1 in two pieces, and Z1 in two pieces, and this is, you get 4, and do it more and more time, finally you get a sum. What the sum is? Here is the sum of all dyadic subintervals of the main interval of the length 2 to the negative n to the initial one. And this is important expression. So what's written here? You take function f, you take a function phi, and averaging over small dyadic rectangle. So this interval, sorry. And this average, because j is small, say without loss of generality, you can think f is a continuous function. So it's like a value of phi of f at some sample point x star. But then you take f inverse. So f inverse and f cancel each other, and you will get like a value of function f at some sample point, and this value you multiply by 1 over 2 to the n, and this since is what? It's 1 to the n. It's a value of this length of small interval, which we can treat like delta x, and this is the value of the length of the large integral. So what's written here is started from here to there. It's just kind of integral sum for the function f. If n approaches infinity, it converges to the average value. So you can see you started from the very beginning with the average of function phi of average, and it goes all the way greater or equal than the average of function I, and this means that you get this inequality. And what is done is so-called induction in scale. So you start with a big interval, split it in two pieces, then chop each piece in another two pieces, and get a bunch of dyadic subintervals, and proceed from larger to finer scale to beta scale, etc., etc. So you get this inequality, which you can write in this form, and this is Jensen inequality. So what's nice about that? We use pure convexity argument and kind of differentiation of integrals arguments. This is why I like Bellman function very much. Personally, half of my life I differentiate integrals. And this is one of the application of theory of differentiation of integrals. Because this statement here, that this is finally converges to the value of f, it's kind of differentiation of integral statement. So it's one of the best probable application of the theory of differentiation of integrals. And now you can see that if phi is really convex, then if this is, we have identity for that function, it implies that f is a constant on interval. Why? Because it means that in this, all the chain, you will change to equality. But equality means what? It means that everywhere we have equality. And if you look at the second line, the passage from the first to the second, it could happen because phi is really convex function. It happens if and only if the value, this value is in fact equal to the middle value. So, and the same story everywhere else. And this means that we had the statement that for any dyadic subinterval of I, the average of phi over small dyadic interval is equal to this number. And this is just a number. It's average of function over large interval. And taking j smaller and smaller, finally you get the statement that phi is equal to f. And it's again pure differentiation of integral statement. Our phi is a constant for almost all t. So you see, if using Bellman function, you prove Jensen inequality easily, and to prove that if LP norm is equal to L1 norm of the function, then function is a constant. And you get just, it's really a very simple and elementary approach, very natural, very intrinsic. So another example, Hölder inequality. So if you want to relate a product integral with just P and Q values from scratch, we don't know any relation between P and Q, nothing like that. We want to relate that integral with Z2 somehow. How we can do this? Say we want to write it in this form. So that integral less or equal some expression which I call B script, which involves Z2. What's the natural way to write B? How we can define this B script? Of course, it should be a supremum of left-hand side, right, if you want to be precise. So the larger value of the left-hand side, which we can get, assuming that this is fixed, this fixes, and that fixed. So it's a very natural thing to do. But unfortunately, in this definition, if you define this way, this function B generally depends on this interval I. Because if it would be independent, you could extend I to the whole real line, and then you will get a rule how to control L1 function via L2, L1 norm via L2 norm, and vice versa on the real line, but they're incomparable. So we cannot do this this way. So we need to adjust it, and the adjustment is to change the integral to average. Just divide by the length of interval, and this is function B. And this function B is, in fact, is a Bellman function for that problem, for Hölder inequality. And this is a definition. So it's a function of two variables, x and y, which is supremum of the average f times g over interval I, such that LP value is equal to little x, and LQ value of g is equal to little y. And x and y are both non-negative. So this is function of two variables, which is well defined in convex domain in the first quarter in a formal way. And it's a Bellman function for that problem. So how we can do this? Very important argument is homogeneity. If you multiply by x by t to p and s to q, you will get this statement just from the definition, if you try to do this from the definition. And then this gives you the other statement, which says that Bellman function B defined this way is equal to Bellman function at point 1, 1 times this expression. So we are almost done. The problem that this could be infinity, right? So if we prove that it's finite, and if we find the value, we are done. We know we found the Bellman function. Okay. So how we do this? And this is a good example which illustrates the general approach which is current. So we take another function B, not B ball, but regular B, which is just a constant C times this expression. So it's not a Bellman function, but we believe that the Bellman function could be selected in this form, could be found in this form. And the problem is to specify C, first of all, to prove that it's finite, and then to specify a value of C. And how we can do this? First of all, that statement implies concavity down for the function B. So it means that we get this finite discrete expression for the B. So if x and y, the average of these 2 points is equal to that point, then for the function B we get that statement, and it follows from that quadratic form is positively definite. And if we try but B is a specific function, right? So we can easily check the condition, and it's actually reducible to the expression that this determinant should be positive. And if you do this computation for this specific function, you will get a right set of parameters. So what's amazing, the methods give us the right set of parameters. We don't care, we don't know, we don't guess. There is no any guess. We just apply an algorithm. We compute, we check that statement, and we get a right set of parameters, which implies concavity, actually. And this means that, well, okay. So now we are looking for the estimate from above, and we need to do induction in scale. And repeating the same argument which we did for Jensen inequality, we came up absolutely the same steps. These are induction in scale steps. So we run the machinery, and after n step, we get some expression which is in fact is integral, kind of integral sums. And even more, you can see that what kind of integral sums it is. And again, if j is very small, and this is again a statement about differentiation of integral. If j is very small, then you take f to some power p averaging over this j, and you can get kind of value of f to the power p at some point. But then you take out take off that p out, and you get a value f at this point. The same story with the g. Here should be q, I'm sorry. And this is kind of a value f at some sample point, value of g at some sample point, times delta x. So this is integral sum. And if n approaches infinity, it converges to the product. So once again, we get the expression from the very beginning. You remember b is a specific function. And what we get, I take the left-hand side, less or equal the right-hand side, which is the top expression, and I know the specific function. And here is c, and here is c. So first of all, you can cancel out c and c, right? And you can take a supremum over all possible f is g, and that supremum will give you a Bellman function to the left. And so this gives us this estimate one, which first of all means that Bellman function is finite, and it's bounded by this expression. And it's actually this expression which you can write this way. And this is a generalized Hölder inequality. This statement is true in averaged terms, and you cannot remove q in general, but if if it's equal to 1, then you can remove denominators. But somehow you get a true statement in a very natural way in doing some kind of procedure. And now if you're looking for the sharp inequality, we want it to be sharp. It means that we want them to get equality on non-trivial function, non-trivial, non-constant function. And if you're looking for this type of property, which means that we apply a minimally convex assumption, then it's plausible to assume that determinant of that form is 0. And if we do that and make a computation, first of all, this expression is just Monch-Ampere equation for this specific function b. And so this Monch-Ampere equation, it occurs naturally in many problems related to Bellman function. And this is an explanation on a very primitive level on this toy model why it occurs. Because we want from the concavity condition, in the concavity condition to add the property that the form is degenerated. And then it's a natural way you get a Monch-Ampere homogeneous equation. And for this specific function, b, it gives you exactly the right set of parameters for which Hölder inequalities is sharp inequalities, 1p plus 1 or q equals 1. Because the previous inequality was good, but it wasn't sharp. It was too much. We required too much. But for this, it will be really nice, delicate inequality. What we can say about general solution, about Monch-Ampere equation. So the problem now is that we know in some way we have proof. One is a proof that Bellman function less or equal to that equation. If you want to prove the identity, we need to show that there is a pair of function g and y, g and f and g with proper properties such that we get the estimate on the other way from below. How to compute it? And again, the methods give us a way to do this. So general solution for Morrison-Ampere equation could be written in this form. And what this form means, if you fix t, and this is number, and this is a number, so this is equation, it's a straight line, right? For fixed t, just straight line. And if you look on the top, for fixed t, it's again a linear expression in t. So it means that fix x and y, then for fixed t there is this line which passes through this point, along which, along this line, function b is linear. So the whole domain is foliated with all that lines. They don't intersect each other. And you will see a nice picture after all. So it's very important. This is from general theory of Morrison-Ampere equations. The whole domain should be foliated by lines along which function is linear. Okay. So, but this is a specific function, and it's linear along line y equals constant times x, right? If you do careful computation, and you will see that because y to 1 over q plus x to 1 over p, and 1 over q plus 1 over p is 1. So it gives you a linear expression. So along this line with this particular choice of t, so choose any t, make this coefficient, and consider this line. This is a line from origin, passing through origin, and go to somewhere. And you can write b is that specific which we get before, in this form. And this is exactly that form which is written above. And if you differentiate in a formal way for t here, and substitute a value of t from that expression, you will get 0, which gives you 2 and 3. This is how we treat this general statement. And so we have proved that, and now we need to prove this one, that Bellman function, real Bellman function, greater or equal to that expression which we found. And it means that in that induction and scale steps, in each step we have identity. Because if such pair of function exists which makes the identity, it should make each step in induction and scale to be change it from inequality to equality. And this is actually a justification why it's called Bellman function, because the Bellman principle from control theory says that a piece of optimal path is an optimal path. So to minimize your expenses in long run, you should to minimize it each day, roughly. So you need to be perfect on each step of your scale. And this is roughly, and this is the same. We need to find the trajectory along which you are perfect. And you are perfect if you are linear, and you are linear along that lines. So to construct a counterexample, we need to use that information about where you are perfect, and you are perfect over lines. And this means that you should find a pair of function f and g such that averaging over dyadic rectangles, which we denote in this way, are related to each other. One of these proportional to the another with some fixed coefficient. So they are on a line that points on a line for fixed k. And this means this is an important picture. So the domain, it's the first quadrant, is foliated by straight lines. And function, Bellman function is linear. Bellman function candidate so far is linear along each line. And we pick some of the line and consider this function. We want to find a function f on g such that xi, xj, and yj, these points are here, right? The positive coordinate x, y, and y, xj and yj. And but if this is true, then it means the following: the averaging of function p over interval g is k times the averaging of q over this small dyadic interval g, and then taking the limit, and it's again differentiation of integral statement, right? We had to the left the value of function to the p equals k times the value of function to the q. And this is the right set for the function to be chosen to make Hölder inequality identity, right? The power p of function f should be proportional to power q of function g. This is a well-known fact from calculus, right? But we get it in a very natural way. Study carefully the behavior of the solution of Monch-Ampere equation. So everything is coming from the general, very general and formal procedure, which works for us. So it's really a machinery. There is no guess in this step. There is well-written algorithm, and we fulfill this algorithm, and we came up, you see, with right things. So it chooses for us all the parameters. We don't care. We just run the machine, and it produces the output. And we just watch what's going on. So, and for that f and g, we have this identity. And so from below, we get this estimate, and we have the same estimate from above. And this means that function b is equal to this expression. So let me outline what's basic steps. And this is kind of the current understanding of the methodology of the approaches, or the approach which we call Bellman function techniques. So the very important things, of course, is setting and scale invariance. So since we do induction in scale all the time, it's very important to have an expression which is scale invariant, inequalities which is independent on the scale. So if you have the inequality on some intervals, the constant should be independent on the interval. Then you can define well the Bellman function. And it's a problem because it means that the operator is good for local operator, like maximal function. But say for singular integrals, real singular integrals like Hilbert transform or something like this, which are defined on the whole real line, there is no scale invariance. So, and it's a big problem for application of Bellman function machinery. And you know that the Martin-Green transform perfectly done with Bellman function, but Hilbert transform, it's a big problem, and it's done in some way, but again, averaging of some dyadic structure like Haar settings involving Haar functions, and because for Haar we can localize it somehow and have some the scale invariance. Okay, the next is concavity. And it's usually not difficult to get after right settings because many of operators, if they are pretty much local, they demonstrate some concavity property, and you can get some discrete inequalities. Then we use homogeneity argument, which helps us to get some additional information about the Bellman function. And then this homogeneity argument, usually we add some, we impose some condition like degeneracy of the Hessian and get PDE, which is called Bellman PDE. And usually, in many cases, it's just Monch-Ampere, homogeneous Monch-Ampere PDE. And from this PDE, we get a solution. And this solution is a candidate, a candidate to be a Bellman function. So, but then we need to prove that real Bellman function is indeed dominated by that solution. And this is a very important part, because to get to that solution, you can do any heuristic what you want. You are free in any methods. You can assume that function twice differentiable, infinitely many differentiable. You can do any informal steps. But when you get the candidate after, you need to prove that it is indeed a candidate. And to do this, you need to run this induction in scale and to prove that your real Bellman function is dominated by that candidate which you find from that informal or more or less informal consideration. And then you know that if it's a Bellman function from Monchon pair, that it has linear orbits. You study the linear orbits, and from these linear orbits, you get a proof of the inverse. Can you give me 1 more minute? Yeah, and this is a current understanding of the technology. And so let me just show in 1 minute what we did with Vasyonin and Slavin for the dupe inequality for maximal function. Just briefly, let me outline that. Finally, we reduce everything to the full boundary value problem. Here is a Monchon pair for fixed z, and it's Monchon pair in 2 variables in x and y. This is a boundary value which is written here, and this is a boundary value for the Bellman function over there. And it's unpleasant because it's a Monchon pair in 2 variables, and there is a third variable which is bad variable. But then, and this is a formal statement, so you need to solve this boundary value problem. But then it turns out that if you use homogeneity argument, you can simplify that, you can change that boundary problem in 3 variables, and 1 variable is terrible variable, to the perfect boundary value problem in 2 variables. And here are 2 variables, a nice convex domain, but it's highly nonlinear, of course. It's PDE, highly nonlinear. You need to solve it, and it's not easy to solve it from general point of view. But fortunately, in this case, again, using that decomposition in using general solution form, finally we were able to solve it. And the foliation picture looks like this one. So this point z divided by q. So solution to that Monchon pair boundary value problems is a function which is linear along these lines and then along vertical lines. And the function looks like this. It's a polynomial part downstairs, and on the first line it's kind of expression when W is, let me show you what the W is. Yeah, here it is. If you take a point x and y joined with a point z over q, the intersection has a x coordinate W. And that W is involved in the definition, in the formula for Bellman function. And this Bellman function was initially found by Melas on 30 pages, pretty tough paper in advance. You see 30 pages, using elementary, more or less combinatorial geometrical arguments. And then we redo it, and mainly you can get everything from 3 pages using Monchon pair equation. So surprisingly, more advanced techniques so naturally shrink all the stuff down, then you can compress it to 3 pages without loss significant information. Yeah. Thank you very much for attention.